So hi, I'm Juha, CEO and co-founder of Quanscient, and I'm super excited to be here presenting our company, our research, and also our ambitious goal of reaching quantum advantage for CFD in the next 24 months. I'll share who we are at Quanscient, what we do in the big picture, but also in more details on how we plan to achieve our objective. But let's start from the beginning. When we were kind of contemplating on founding Quanscient, we actually drew or wrote on a napkin that let's do something cool with quantum computing. And I personally thought that that's a brilliant business idea, but even with all the positive fuss around quantum computing, that somehow wasn't enough to convince the early stage investors. So we went back to the drawing board and decided to go with what we know best, which is multiphysics simulations. And a little about Quanscient. So we're based in Finland, therefore in good company. There's a huge growing quantum ecosystem there, of course led by IQM, one of the leaders in quantum computing in Europe. And so far Finland has mostly been known about rally drivers and Formula One drivers, but I hope you can add to that list quantum computing companies very soon. And actually it's 19 employees since Tuesday. And yes, we really like hyphenations. So here's our founding team. As said, I'm working as CEO. I mostly have my background in leadership roles and business roles, but also some software engineering. Alexandre is our CTO. Alexandre did his PhD in the University of Liège on the topic of how to scale multiphysics algorithms in the cloud by distributing the computation. And Alexandre at the moment leads our classical side algorithms development team. Asser also has a background in multiphysics simulations, but since then he's been working as an entrepreneur in his previous startup as a full stack developer, and Asser is in charge of all the cloud infrastructure and the user interfaces. And then Valtteri, probably the most important person in the context of this talk, has done several postdocs around the world in Boston, Montreal, Bologna, Tampere, and most recently in Aalto University as a quantum researcher, and he leads our quantum research team. So, okay, talking about simulations as kind of the topic of the talk probably suggests it's not about flight simulators. It's about multiphysics simulations, which includes also computational fluid dynamics. So what are multiphysics simulations? Just a short summary. Basically, computer-aided engineering tools where the engineers can, for example, on the picture on the left, there's a CAD design of an electric motor. They can export that into a multiphysics simulation platform and actually simulate how the device works in real life. And talking about electric motors, that includes computational electromagnetics, how it works electromagnetically, fluid dynamics, how it works thermally and how that affects the electromagnetism and vice versa, and solid mechanics simulations, how the structural integrity holds on. So multiphysics. And the key advantages, of course, are that before committing time and resources to building prototypes, the engineers can do validation with simulation. So they're also called digital prototypes in some contexts. Okay. What? Sorry, there seems to be a problem with the slides. All right. Seems like I only have the starting few slides here. Let's see again.
Was there supposed to be more slides, or?
Yes, but no
Okay,
worries.
okay.
Let's just go without them then.
Okay.
So-
Do we have any questions for you quickly?
I can, of course, continue on the
Oh, yeah,
without the
sure,
slides.
yeah.
So,
Go ahead,
so
yeah.
no worries there. So, talk about the multiphysics simulations. What we already have is that we have released a cloud-based solution for that, and that provides us the capabilities to run multiphysics simulations over 100 times speedups. and solve over 100 times more complex problems than with current existing products. And as we are cloud native, we can also run practically an unlimited amount of simulations parallelly, enabling engineers to run hundreds of variations of their designs each day. And this also matters because this has the capability to produce massive volumes of simulation data that could be fed into machine learning algorithms and to, for example, build surrogate models of the designs, or even create AI-based algorithms to provide design improvement suggestions for the engineers. But okay, so far I've been talking about the multiphysics side. Let's dive deeper into the computational fluid dynamics and what we're working on that with quantum. So traditionally, when building physics simulations, the algorithms depend on linear solvers. So in that case, we typically take some kind of discretization method, like the finite element method or the finite volume method, and then we end up solving partial differential equations, right? Well, when doing this with quantum, we'll need some kind of quantum linear solver. So the two existing most popular approaches to this are HHL, but practically that requires fault-tolerant quantum computing, or the variational approach, which is feasible with the Niskera computers. But the main problem with both of these methods is still the data input and data output. For example, you cannot input an arbitrary matrix to a quantum computer, and you cannot really read out the full solution. You can extract global properties, like for example the integral of the solution, which can be useful to a degree, but still introduces some lacking in the usability of the results. So we have put our focus on methods that we call quantum native. And one of the examples of this is the quantum lattice Boltzmann method, which is kind of our flagship method. And I'll explain a little bit about the lattice Boltzmann and also how we apply it with quantum. Now, by quantum native, we mean that we strive to encode the physics directly to the system, so that we have a direct analogy between the physics problem and the evolution of the quantum computing system. And with the lattice Boltzmann method, it's recently been gaining also in the classical side a lot of traction for solving large-scale CFD problems. And okay, let's talk about how we do it with quantum. So typically for CFD, you have two ways to solve them. So I mean, you can go with the linear algebra way, solving Navier-Stokes equations, so directly solving things like velocity and pressure, etc. Or you could go particle-based methods, so simulate these effects directly on a particle or molecular level. Quantum could be helpful there as well. But with the lattice Boltzmann method, you're working on a mesoscopic scale. So basically, we create these imaginary particle densities and aim to model their behavior. So we simulate the probabilities of the particle densities. So for example, for a one-dimensional lattice Boltzmann simulation, we would simulate what is the probability of a particle moving either to the left or to the right. If we add more dimensions for 2D, for 3D, that increases the directions that the particle can move, but the principle is the same. And for quantum, the key advantages for this are that these probabilities of the particle movement can be encoded directly into the qubits of the quantum circuit. So basically, it means that we can increase the size of the lattice or scale of the simulation exponentially as the number of qubits increase. And another key advantage is the input of the data. We can run the simulation with minimal data encoding and let the system evolve. So, for example, if we start with a zero velocity field for CFD, we can get by with very minimal initial data encoding. And also for reading out the data, the qubit measurements correspond directly to the probabilities of densities in the lattice, and this data can be turned into the full solution by a simple summation calculation. Now a little bit about the results that we've been able to achieve with this. So last summer we had a major breakthrough by being able to run a quantum lattice Boltzmann algorithm using real quantum hardware. That particular algorithm was a 1D advection diffusion effect simulation. So what that is, for example, if you drop some ink into water, advection diffusing effect simulation simulates how it dissipates.
Found this the slide, so if you
All right.
want to skip ahead to wherever you are
I'll
now,
skip to where
if that
I am.
works.
Thank
Sorry
you.
about that.
No worries. So yeah, there's just a summary of the kind of two approaches, the linear algebra and the quantum native, and kind of this visualizes the lattice Boltzmann method and the movement of the imaginary particles. But yeah, where I was at was the results. So advection diffusion effect, dropping ink into water, how it diffuses. And if we think about 1D advection diffusion effect, we would, well, take, for example, a stream and then abstract it into a one-dimensional channel and see how that dissipates there. And we ran the experiment initially with Quantinuum's H11 computer, but later we have reproduced the same accurate results with, for example, IBM machines. And on this slide, nice to be able to point to them. So on the on the bottom right picture, that actually represents what we measured from the qubits. So the probability distribution of the particle densities for the 1D ADE simulation. And in there, the dotted line is kind of the ideal solution, the reference solution that we ran with Qiskit AER simulator, also validated with classical algorithms. The blue bars represent what we got from the H11 simulator that kind of simulates the hardware as accurately as possible, and the red bar is what we got from the hardware. So it is a very good match with the actual ideal solution. And the key innovation in how this was done was the optimization of the algorithm. So our algorithm, as said, scales exponentially in the size of the lattice, but with the optimization, it grows logarithmically in the number of gates required, or the depth of the quantum algorithm. And for this 1D advection diffusion effect simulation, we needed 7 qubits, but as we can grow exponentially with, let's say, 60 to 80 qubits, we can start pushing the limits and the boundaries of what can be done with classical hardware. And for reference, that would take about 580 to 750 C0 gates for the depth of the algorithm. And this gives us the confidence that we can achieve quantum advantage for CFD in certain use cases within the next 24 months. So a little bit about our quantum roadmap. We're now working towards extending the hardware experiments from 1D to 2D and 3D, and also Navier-Stokes equations or 3D turbulence model simulations. But as said, within 24 months, we believe we can demonstrate quantum advantage in terms of performance and build toward a more generic quantum acceleration from there. And eventually provide more generalistic multiphysics simulations that are infeasible to solve on classical hardware. And kind of looping back on the big picture, on what we're building here. So the technical vision is to build a multiphysics simulation platform that combines cloud and quantum computing in a hybrid solution. So eventually the end users wouldn't even have to know if their simulations are being run on cloud or quantum technology or a combination of both of these. But before we get there, we're now focused on partnering with quantum hardware manufacturers, but also end user representatives to collaborate on bringing these capabilities to reality. And finally, there's the QR code contains a link to our online quantum demo. It has a lot more information on the lattice-Boltzmann method, how we apply it. It contains the quantum circuits for the unoptimized algorithms if you want to take a look, and also an interactive demo where you can run these simulations, albeit they are run on a quantum simulator in the background for, well, obvious practical reasons. So, thank you so much for your attention, and please come and have a chat, either after the talk or at our booth at the exhibition area if you'd like to know more about this. Thank you.
Thanks very much, Juha, and apologies about the
No worries.
Technical issues. Do we have any questions? I was wondering, or have you done any maybe error mitigation to improve the results? I mean, the hardware results that you showed looked quite good, but have you thought about that?
Yes, so we have, of course, in terms of the algorithm optimization, like minimizing the gates, but then also we have worked in collaboration with, for example, Q-Control, their FireOpal platform to handle, and that's actually what enabled the positive results on the IBM machines.